All right, so this is problem 7 on the practice test for Unit 5. So we've got air enters an air conditioning unit at 10 degrees Celsius, 70% relative humidity at 10 meters cubed per minute. So I went ahead and kind of drew up a diagram here. So that's the state of our moist air coming in. It's heated to 20 degrees, so there's state 2, and then it's humidified with steam exiting the unit at 27 degrees Celsius and 30% relative humidity. So the first thing that I'm going to do is I'm going to recognize, number one, that this is a simple heating process. So simple heating, in other words, just like for a simple cooling process, that specific humidity does not change. And so that's going to help me figure out how to draw things on my psychrometric chart when I go to do that. And then this guy right here where I'm injecting steam is just simply a humidification process. So not really much I can say about that, except that, of course, your humidity is going to go up. But other than that, that's kind of it, right? I can't say things like the wet bulb temperature is constant. That's only if I'm injecting liquid water, and in which case it would be an evaporative cooling process, right? As long as I didn't have any heat transfer for that evaporative cooling process. But anyway, all right. So let's go ahead and draw things on our psychrometric chart. I've got it down below, and let's use pink. Feeling good about that, I think. Okay. So here we are, state 1. So I forgot already. I need my problem statement. Hold on, what? So 10 degrees, 70% relative humidity. So here's our T1, and then 70%. So it's this guy right there. So it looks like that's our state 1. And then we heat things up to 20 degrees, and we're going to do that along a line of constant humidity. Perfect. And probably at some point I'm going to need this value. So kind of, yeah. So specific humidity at 1 and 2, approximately 0.0055 if we need it. Okay. So, but anyway, there's our, draw a little dot. There's state 1, there's state 2, and then state 3, we're humidifying things, but we have enough information to put a dot there. So coming out at 27 degrees and 30% relative humidity. So there's our 27 and 30% relative humidity. Okay. Gotta help myself out here because it's hard to see. It's like about right there. Put a little dot there so I can better see it. So there's state 3. And if I wanted to get that guy about 0.007. Okay. And then if I need the enthalpy, I'll probably need those at some point, so might as well. I would say this is probably, gosh, I can't see. Let's use this actually. Go away, you. Go away, you too. Let's see. Okay, maybe like 24, I'd say. So just kind of trying to help myself. This guy, there. So that'd be 1, 2, 3, 4. So that's about 34. I'll probably need one for here. Gosh. So 2. I mean, maybe it's a little above 44, but we'll call it 44. Yeah, if I need those values. I don't know. So 44, 34, 24. That works out well, doesn't it? All right. So I drew the process on the psychrometric chart and then sort of preemptively noted what some of those values are. And now I need to figure out what the rate of the heat transfer is. So Q dot. So let's apply mass balance. So I'm going to apply my mass balance. I'm just going to look at this section, I think. So if I do that, m dot A, m dot A1, m dot A2, they're the same. We'll just call them m dot A. And then, of course, for the water vapor, you got one inlet, one outlet. So m dot V1, m dot V2, both of those are the same. And so we've seen it before where if we apply our energy balance, your dE dt, right, that whole long equation, dE dt equals Q dot minus W dot equals the sum of the m dot h's plus the kinetic energy plus the potential energy, all coming in minus the same thing going out. Everything is going to go away except for your Q dot and then your sum of the m dot h's in and out. So I guess that kind of do have to make some assumptions, right? Steady state, changes in kinetic energy are 0, changes in potential energy are 0, W dot's equal to 0. Other than that, that's kind of it. I guess also we're assuming that the vapor behaves as an ideal gas, the air behaves as an ideal gas. But again, other than that, that's it. So this is going to be some of the stuff going out minus the stuff going in. All right. So I'll go ahead and kind of go through the derivation here, but so it's m dot A HA2 plus m dot V HV, and this is all at state 2, minus the same thing at 1. And then what we do is we just sort of isolate m dot A on the outside. So I have HA2 plus m dot V2 over m dot A, which is just our specific humidity. It's all at 2, and then the same thing, of course, at 1. All right. I have the volumetric flow rate. Probably want to put that, this guy, if I say that this volumetric flow rate is the same as the volumetric flow rate of the dry air, which we've done that before. We did that for the previous problem on this practice test. Then we would put that mass flow rate in terms of V dot A over the specific volume of the dry air. So this would be V dot A1, that 10 meters cubed per minute, over our specific volume at 1. Okay, bring this down. So this is at 2 minus the same thing at 1. And I know we're kind of running into stuff, but it's okay. All right, almost there. So this guy is going to be 10 meters cubed per minute. And then we had already figured out what the specific enthalpies were. So at 2, we said that was 34 kilojoules per kilogram. At 1, we said it was 24. So 34 minus 24, both of these guys are going to be in kilojoules per kilogram of moist air. We do need to figure out the enthalpy of that, or the specific volume of that moist air. So get rid of these guys. So there's a 0.8, there's a 0.85. So each of these is 0.01. So it looks like we're really, really close. That specific volume is really, really close. You could see to 0.81. I mean, we could sort of split hairs. Oops. We could, oh, being annoying. We could split hairs and say it's, I don't know, a little less than 0.81, but I'm going to say it's about 0.81. So 0.81, this guy is meters cubed per kilogram. Um, so this is just kind of plug and chug here. So I've got 123.5. Again, on a test, so this is kilojoules per minute. And I'm seeing there was I had put kilojoules per kilogram on my answer sheet, but that's clearly not what this is. It's a rate, and it will be in terms of kilojoules per minute. All right. So that's going to be part B. And now we just have one more thing. We need the mass flow rate of that injected steam. And so for this guy, I'm going to do just, I think really the only thing I need to do a mass balance on this guy, right? So just a mass balance. I'm going to do just a mass balance on the second part, on the humidification portion. So let's do that. Right. Actually, so this is an energy balance and a mass balance on that kind of blue control volume. And then we'll do a mass balance on this yellow portion. Yeah. All right. So air is nothing new, right? One inlet, one outlet. But for the water, we do have to be careful. So the steam, so you'll have water vapor coming in at state 2. Oops. And then you'll also have your m dot of the steam. And then that's going to be equal to our m dot v3. And so of course you can rearrange and solve for that m dot st. So this is going to be m dot v3 minus m dot v2. We've put this in terms of mass flow rate of that dry air before. So right, because it would be the same as saying m dot a on the outside of those parentheses times m dot v3 over m dot a, which is the specific humidity. All right. Well, if I look at what that mass flow rate is, you could see it's just 10 divided by 0.81. So we do have that information. So what's 10 divided by 8.81? I don't know. I was hoping it was written down somewhere, but I guess not. So 10 divided by 0.81, 12 point, oh, look at that. 12.3456.7. Oh, it was almost perfect. Jumps to 9. So, but this ends up being 12 point, like I said, 3, 4, 5, 6, 7. We'll leave it as 0.35. We'll round it to 0.31 to 0.35 times our specific humidity. So let's see, and we had made a note of those, didn't we? So looks like it's going to be 0.007 minus 0.0055. So oh, there we go. So 0.007 minus 0.0055. And we got something like 0.0185. And the units there are going to be in kilograms per minute, kilograms of water per minute. Yeah, because this mass flow rate is also kilograms per minute. So, all right. So I think let's actually make this a little bit, there we go. So if you wanted to take a picture, get the whole piece of it, you can do that. All right, let me know if you have any questions, and thank you for watching.